Ladies and gentlemen, I'm Henk van Houten, the CTO for Philips. I would like to welcome you to this very nice event, also on behalf of Eindhoven University of Technology, and Signify, as well as Philips, because we collaborate in organizing this symposium and in actually organizing the Gilles Holst Award. We are very honored to have Dr. Michael Grieves here today as our Holst Lecturer and recipient of the Holst Memorial Lecture Award. I'd like to explain a little bit where this Holst Award is coming from. So this is Mr. Holst. Dr. Gilles Holst got his, actually worked on superconductivity in Leiden with the famous Kamerling Honors, who got the Nobel Prize for the discovery of superconductivity, and that work was partially also based on the work of Gilles Holst. But he's remembered more because he actually founded the Philips Research Laboratories here in Eindhoven, which was at the cradle of a lot of new industries that Philips created, and also, I think, of the Brainport region in a way that has emerged here in Eindhoven. So he led Philips Research between 1914, more than 100 years ago, and 1946. And he was always very interested in the interaction between industry and academia. And he actually helped found also the technical university here in Eindhoven. Because he found that very important, not only to have a collaboration partner, but also a source of talent, of course. And I think that from that day, we have always worked very closely together. And it was not only Philips and the technical university, but the technical university created also collaborations with a lot of other smaller and bigger industries in the region, and as such has become a motor for the economy here. And what we call Brainport today is one of the hotspots for innovation in Europe. Now, Holst was also a remarkable person. He had a lot of strong opinions, and he also impressed a certain character on the laboratory, but also on innovation, and he will be remembered for that. Now, let me tell you a story about Holst that you may not know, and I think it's relevant to the theme of today. And the theme of today is digital twin, right? Now, one of the famous statements of Holst was, "I do not like cast iron." And that was an interesting statement because he was leading a laboratory working on material science and physics at the time. So why did he not like cast iron? Well, the reason was, you cannot really control the material properties of cast iron. So you cannot make it very predictable. And as a result, when an engineer designed a bridge or a large piece of equipment that would be built using cast iron, after carefully calculating what the minimal thickness of the metal should be, etc., he had to put in a kind of fudge factor, a safety factor, to actually make sure that the bridge would hold. And maybe even a factor of 2 or 3. So that is why Holst did not like cast iron. He liked the idea of being able to scientifically underpin how some device or a product worked, and also to have a model for it. So that is actually, I think, the mentality that is behind the idea of the digital twin. So product design that can be based on a scientifically underpinned mathematical model, so that you can design your product in a reliable way, first time right, and actually even use that model during the lifetime of the product to gain information on how it's functioning, how it's perhaps deteriorating, to make sure you can do preventative maintenance and all of that. So I think he's a worthy name to also give to the speaker of today. The first Holst Memorial Lecture was delivered almost 50 years ago, 1977, in the same lecture hall by Alexander King. And he was one of the founders of the Club of Rome at the time. And as you all know, the Club of Rome was one of the first organizations that was raising the alarm bell around the global environment, and that we should be really aware of taking care of our environment, of our planet. And so this interaction between innovation, academia and industry working together, but also addressing societal challenges, has been a little bit of the red thread behind the programming of this Holst Lecture Award. And I think that digital twinning and its impact on industry as a central theme for today's Holst Lecture fits this very well. So, ladies and gentlemen, let me now say a few words about the Holst Memorial Lecturer of today. Dr. Grieves earned a Bachelor of Science in Computer Engineering from Michigan State University, but also he has an MBA from Oakland and a doctorate from Case Western. He introduced the highly influential concept and model of the digital twin in 2002, so 20 years ago, at the Society of Manufacturing Engineering conference. I think that what he did is really establishing the concept of digital twin as the fundamental conceptual model underlying product lifecycle management, but also as part of the digital transformation of the entire value chain from R&D to manufacturing to maintenance of complex systems. And Dr. Grieves did not stop with the bare bones concept of digital twin. He also became the expert linking that concept to data and AI, which enriched it a lot. And he also didn't only work on this as an academic, where he has gained a great reputation, writing also seminal books on these topics. No, his impact reaches far beyond that, because he was applying his deep expertise to industry and commercial practice through consulting to top global companies like NASA, Boeing, Unilever, Newport News Shipbuilding, and General Motors. He also has been a senior executive at various Fortune 1000 companies, as well as smaller entrepreneurial organizations. And he founded an innovative systems integration company and took it public successfully. And he didn't stop there. He was just telling me over the break that after that he could have retired, but he was not successful at it and really kept working. So I will now no longer keep you from the exciting lecture that we will hear, for which we have gathered. So Dr. Grieves, the floor is yours.
Good afternoon. Good afternoon. I'm not the only one that's going to be working here this morning. Okay, technology's working, great. So I'm going to talk to you today about the digital twin, and I really believe that it's going to drive 21st century transformation. I mean, we are at the cusp of transforming society quite a bit in terms of doing this. And so to your comment about Dr. Holst is that today he wouldn't like additive manufacturing, same problem. So, I sympathize with him. And my contention is, if he had a digital twin of cast iron, he could have supported it better. But too late for him, right? So I want to show you the first slide for digital twin, and it didn't even have a name. It had the conceptual ideal for PLM, and in fact, just to set the record straight, the actual name, I called it an information mirroring model. I called it a few things. But my colleague at NASA, John Vickers, actually coined the term and used it in a NASA roadmap in 2010. And in fact, I had that in a footnote in my book, and it was such a good name that's what it became from that point on. Couple other quick things is, one is, and I'll show you the model as it exists today, but at that point in time, you can see the little sub-models under the virtual twin. At that point in time, people didn't really realize that you could have the same environment in digital and virtual systems that basically would allow you to build the same car and crash it over and over again. And quite frankly, in the physical world, you do it once and you're done. So I pointed that out. It got dropped in later ones. The other piece that I wanted to mention is people keep talking about the fact that I applied it to manufacturing. Quite frankly, this was about service, and it was about being able to service the product after the vehicles were out running around in the world. I did apply it to manufacturing companies, but it was really in terms of the product life cycle. But the key thing here is that it was to underline the whole product life cycle right from the beginning. I mean, it was not to be just simply design, wasn't manufacturing, wasn't support. It was to underpin the entire life cycle of the product and being able to support it in a fashion that you needed to support it. the model as it exists today, much better graphics from my friends at NASA where I was a consultant. So we spruced up the model quite a bit with some good graphics there. But the three major pieces of the digital twin is on the left side you have the physical item in physical space. And quite frankly, as I sort of kind of keep focusing on, is that it's not only the digital twin of the item itself, it's the environment that it exists in. And you heard from Ewan about his situation. It's not simply a ship, it's a ship in its environment and knowing where that is. And so the environment piece, this is not simply an object hanging in space by itself. It's the environment forces that act upon it and that it acts upon that are critical. The virtual space, so this is where our digital models are, and they're on that side of it. And that's the focus of the fact that not only do I have to model and simulate the actual item itself, but I also want to simulate and model its environment. And then the third piece there is the fact that I collect data from the physical world that populate my virtual world, and then I want to use the information from that virtual world and be able to use that in the physical world. That connection is called the digital twin. I am not a fan of the term. I've hung on by a twin too often by a thread too often in my career. And so I'm not a fan of digital thread, but we're sort of stuck with it, and we're going to have to deal with it. But that's the thread. It's a communications thing. It is not a repository of information. It allows me to communicate back and forth. This is really sort of caught on. I mean, I'm sort of amazed by how rapidly this is. We're looking at sort of exponential rates of the number of times that it comes up. About 2018, I did a podcast, and I said there were 1 million hits in Google. I just looked at it the other day. There are 5 million hits on digital twin. So we're really seeing it exploding in terms of how people deal with that. And why do we want to do that? The reason we want to do that is, this is where the transformation comes about, is that we want to move work activity from the physical world into the virtual world. And why? Because we want to be able to trade off atoms for bits. Atoms keep getting more expensive at the rate of inflation, which is really going highly today, but bits are basically decreasing at an exponential rate. So even if it's even today, in 10 years, bits cost you pretty much nothing, while the cost of the physical world has increased pretty dramatically. So that's sort of the reason why we want to do that. And I want to just spend a few minutes talking about the underlying premise for digital twin and also for digital transformation in general. And this is the idea of the fact that information is a substitution for wasting time, energy, and material. And so this kind of comes from the idea of substitution sets from Giddings and Constitution of Society, which is if you want some reading to put you to sleep, that's a good book for you. But the whole idea of the fact of human life is pretty much the fact that we are goal-seeking activity with minimum physical resources. I mean, that's what we do pretty much in our entire existence. And so if we're looking at sort of designing a product, knowing what product is going to work for us, whether we're wasting our resources doing that. In fact, not knowing the fact that the product's never going to work is a really good idea, because you'd waste all the resources if it doesn't work. I mean, the example I use is, getting 3 kids to after-school activities. I mean, I look at wasting time and material. It would be good to know that practice was canceled or that the field was moved. And so if I was omniscient and omnipotent, I would only spend the amount of physical resources to do what's in that green section. And since we live in a capitalistic society, we can cost that out. We can cost time, energy, and material. Everything above that is what I call information inefficiencies, and it's wasted physical resources. And so there's been a lot of work in, obviously, information theory, and I'm a computer scientist. But the concept of information, one thing is, this comes from a book from an economist, a Nobel-winning economist, is one thing is certain from the literature. There's no consensus, no clarity, but plenty of confusion about what information is. So I want to focus on what information is. I want to focus on what it does. And what it does is this replacement of wasting resources. Now, what the premise of information is that information is not a substitute for the physical resources that I need to do to basically deal with the minimum resources I need to do my task, but it can replace information inefficiencies. Now, I'm showing it replacing all information inefficiencies, and that's not ideal. But to the extent that I can not make mistakes, and if I had information about certain things, I would basically make different decisions, are going to basically what drives that. And the way this works, and the reason those of us that have been in the computer industry have been successful, is that it needs to be that the cost of information, because information is not free, it costs something. And unfortunately, we don't have a unit of information, but you can get there with a proxy of the cost of hardware, software, people's time, and collecting data and turning in information, is that the cost of that information is less than the cost of wasting resources. And that is the whole premise of why digital transformation, and certainly the digital twin, has garnered so much attention, is being able to create value using this proposition. So I'd like to kind of spend a second talking about, why is this so important today? And the answer is that I'm sure you should all be familiar with Moore's law, but the exponential increase in computing capability is what's driving that. I mean, we passed 54 billion transistors on a chip. In the early 70s, I had, I don't know if the privilege, but the pain of having the Iliac 4, which was the first supercomputer, report into me. And it was a size, in fact, maybe bigger than this room. It was designed for about 25 megaflops. Today, an Xbox has about 12 teraflops of processing power. And by the way, it's, what an Xbox looks like, it doesn't take up this whole room. And so this is what's driving where we're going with this is our ability of being able to do that. My projections, and it's a little it's a little tough in terms of saying it's Moore's. I mean, people are saying, well, Moore's law is going to end, but they've been saying that for a long time. In 2030, we're going to have 7 trillion transistors on a chip, and in 2040, when am I computing? 885 trillion transistors on a chip. So we have, if we looked at this as a normal curve and not logarithmic, we basically hit we hit the asymptote and we're going straight up. And so we need to be looking at what can we do with this kind of computing power in the future, and where is it going to be going, and what kind of capabilities we have. And certainly from the digital perspective, digital transformation and digital twin, we're going to have huge amounts of computing power to do some of the things that I proposed. So what's sort of fascinating is, what is the scale and scope of the digital twin? And certainly you saw, a great presentation about a digital twin of people. Now I want to sort of focus on the fact that, and I'll talk about this a little bit later, is that this is a digital twin of the physiology of the people, okay? I don't think that we're ever going to be able to have computers that are replace people, but certainly from a physiology standpoint, we can have digital twins of people. But, we started with automobiles, ships, power transmission systems, airplanes, oil rigs. In fact, I saw a great presentation last week of the ADNOC, which is an oil company that basically has a complete digital twin of their oil field, their pipeline, and their refineries in one single digital twin that basically gives them all information. They figure $1 billion in 3 years on it. There's a paper that came out last week that said the projection for oil and gas is to save $1 trillion over the next 10 years. So there's huge, huge value here in digital twins and digital twins of tangible things. But we're seeing also digital twins of cities, There's been a number of papers of digital twins about COVID, and either in managing COVID or the pharmaceutical companies being able to design the vaccines for COVID. Digital twin of the Earth. I just saw a paper of digital twin of the oceans. So if you can imagine it, we can have digital twins of it. So it doesn't have to be simply tangible things. If it's an intangible process that you can basically be able to see in this, you're going to basically be able to have digital twins. So digital twins of logistics, process industry, economic systems, manufacturing processes, and supply chains. So if I can imagine it, I can create a digital twin of what that's going to be. So in fact, intentionally, I only talked about tangible stuff to begin with because I didn't want to confuse the issue. But I think huge value is being able to have digital twins of things that we view as intangible. I want to spend a few minutes talking about digital twin types. So the types of digital twins we have, and again, remember that my basis of this is that it underlines the entire product lifecycle. One of the opportunities here, as you can see from that little thing, is to move from a functional-centric view of the world where we siloed information depending on what area you were in, engineering, manufacturing. I mean, classic problem in industry was engineering would design a product, throw it over the wall to manufacturing and say, go build it. And the manufacturing people are scratching their head thinking, if you only had talked to us, we could have done this in a much quicker and better fashion. And so what we want to do is to look at a product-centric view and be able to populate and consume the information of that across the entire product lifecycle. I mean, that's really what works in terms of being able to be able to be more effective and efficient. NASA had this joke that said, faster, better, cheaper, pick two. I think we can pick all three of them if we basically look at a product-centric rather than a functional-centric view. So the first type of digital twin is what I call the prototypical digital twin. And you can see that basically, it starts off very faint, it's an idea, and by the time you get to the end of this phase, the engineering and design phase, is you have a physical manifestation. And so the focus here is I want to basically get the product and create the product virtually. In fact, in a World Economic Forum article back in about 2015, my colleague at NASA said, what I want to do is I want to design the product virtually, test the product virtually, manufacture the product virtually, support the product virtually, and only when I get it all right do I want to go out and move expensive atoms. And so there's huge value of moving work into virtual space as a digital twin at this phase of the life cycle. So in the create phase. These are all the products that can be made. And so these are the products that I want to make with the variants. So this is a generation of products, and this is the information about how they're made. When I start to manufacture products, when I start to make things, I want to have a digital twin instance of that specific product. And so each thing that comes off the assembly line will have its own digital twin that then stays connected to it for the entire rest of its life. In fact, this will exist even after its life is over. There's a sort of a story where one of in fact, it was at JPL, they were looking at doing a new probe, and he's sitting the guy sitting on his desk with his feet up on his credenza, and he sees people throwing out stuff, and he said, what was that? And it was from the previous probe. And so he ran out and dumpster dived in order to be able to pull information from a previous version so not to have to create the wheel. So there's value in this information. What I want to tell you is that it depends on the complexity of the product whether I'm going to have a digital twin instance or not. If I'm doing a paperclip, I don't need a digital twin instance. If I'm doing an F-35 fighter or a power generation system, then I'm going to need a digital twin instance, and I want to connect that throughout the entire life. Where we're going to see real value, so these are all the products that are made. Where we're going to see real value is what I call the digital twin aggregate. And this is if I take all the information about the products that are out in the world and collect that information, I should be able to do things like prognostics, and be able to predict performance of that product. So these are all the products that are made. And so I want to look at the fact of collecting this. I can use Bayesian probabilities to understand how those products work. What I really would like to do, when I have a kind of a paper from Industry 4.0 that says their focus, and by the way, they've changed this subsequent to looking at digital twin stuff, but their focus was when time I have a problem to the time I remediate, I want to collapse that. What I want to do is I want to get rid of having the problem entirely. I want to be able to predict that performance and be able to predict that in 4 hours, if I keep doing what I'm doing, I'm going to have this problem, and I'm going to basically be able to fix that. So I want to kind of next sort of talk to you about, so this is the four. Now, what's great about the digital twin versus a physical thing is that with a physical thing, it's all or nothing proposition. I either possess it or I don't have it. The information is granular. I don't have to have all it in the same place. I can basically use, for example, information from the digital twin prototype for the digital twin instance, and I don't have to reproduce it. So I can logically pull these things together in order to be able to create value. So how does this work throughout the entire life cycle? I mean, I've said it's the underpinnings of it, but what does it really look like? Well, and this is sort of the digital twin model in the create phase, and it's got the three required elements: physical, virtual, and the thread that connects them. But I also need to create the digital twin of the means of production. Doesn't do any good to have pretty pictures of something I can't make, okay? And again, classic manufacturing, we've had this particular problem of being able to create these things and then we can't manufacture it. So I want to basically be able to manufacture the product virtually and support the product virtually before I actually start to move around expensive atoms. And by the way, I build in about 85% of my costs at this particular point in time. So it's critical I get this right. So I use the digital twin prototype, the prototypical digital twin at this stage for not only the product itself, but for the means of production. When I start to manufacture it, this is the most complicated phase of the life cycle, is not only do I have to in essence, come up with the physical product from my virtual plans, I got to basically be able to use that means of production in my virtual machines that tell my physical machines to go make it in a certain particular way. Now, for those of you that are going to be graduating or have entered the workforce pretty recently, if I can really get to additive manufacturing, I can just print this stuff, and that's going to be really easy. But I basically have to take the bill of process, and I have to basically feed that into my machines in order to be able to create from my virtual plans of the product itself to create the physical elements that are manifestation. I got an argument with the president of PTC who said manufacturing is a function of engineering. I said, au contraire, is that engineering is a function of manufacturing. My intent is I manufacture it and hope to hell I come up with my original design. And so that's, that's really a difficult thing, but we can do this better, I think, if we use digital twins at this stage. So I'm going to use my digital twin prototype, and I'm going to use digital twin instances. This is where I create my instances of my complex products to follow them out throughout their entire life. And then finally, I basically have the sustain phase, which for certainly industrial products can go decades and maybe even longer in terms of having that product in use. And I want to keep the products that I make in connection with their digital twin throughout their entire life. Why? Because I can go interrogate those products at any particular point in time and be able to no matter where they are in the world, be able to know exactly where they are. I mean, one of the things I'm sort of fond of saying is there'll never be another Malaysian Airlines problem. I mean, we know where every airplane is, and we know what it's doing because it's transmitting on a constant basis, okay? So its digital twin will tell us where these things are. So there's huge value in terms of doing that, not only from replication, understanding what those are, but in terms of production. So the missing link here, so we're using not only the digital twin prototype, the digital twin instance, But also then, as I said before, we're aggregating that information in order to be able to do prognostics, prediction. We can apply AI to it to look at it. I'd love to have causation, but I'll live with correlation if it can basically predict fault failures. If I see this sensor, this sensor, this sensor, I have an 80% chance of having a failure in that component. I want to replace that component before it actually fails. So I don't want product failures, I want to predict it. The missing element has been in kind of traditional is that the link between the user doing this and working with this and the engineers has not been there. I see generation after generation of a product that has the same particular problem that's been fixed in the field. Why? Nobody ever told the engineers. Your assumption about that is incorrect. So this allows us to close that loop and be able to feedback the life of the product's information back into the beginning phase. So the next variant of that, or maybe the next generation, won't have the same problems that we had before. I want to briefly run you through a fallacy. I see this less, but it's still an issue. There's, in fact, a position paper that came out of AIAA that basically says you don't have a digital twin until something rolls off, a tail number rolls off the assembly line. And that's a fallacy. As you can see, my focus is that it underlies the entire product life cycle. And the first reason is that the twin metaphor is not understood. Everybody thinks digital twin is like digital people, is a people thing, and the twins have to be born at the same point in time. They don't. All it requires is duality and similarity, but it doesn't require timeline simultaneity. And the example I'll use is that if you come in with a weak excuse and I say, boy, that's the twin of the excuse you gave me a month ago, it's still a twin. I mean, we understand that. You didn't have to say both of those at the same time. So the twin gets confused because people think that they're two humans. It's overspecified. The secondly is that the digital twin framework was meant to be for the entire product life cycle. So as soon as I intend to have a product, that's what differentiates it from having a model or a simulation and having a twin. I'm going to make a product out of this thing. The DT actually exists prior. Nobody walks into a factory, pounds metal, and says, gee, I hope a plane comes out of here, okay? I mean, the work in terms of doing products has been done, at the beginning. And the issue of it is that it's not just semantics. How we talk about things is how we think about them. So if we have a different name for first phase of the product life cycle, it means that we are not having the same conversation with the manufacturing people or the support people. And the poor support people generally really get the tail end of this thing because they're not dealt with it. So the digital twin always exists, but if it has a different name, it's a digital systems model, I've heard some other things. But it basically, it decreases our ability, and what happens is that it regresses to being functionally siloed. Again, the whole idea of digital twin in product lifecycle is to be able to have this product-centric perspective of the information that exists across the entire life cycle. And then finally, it's just inelegant. It's ugly. If you have different names for things, you're never going to get common. So common language, common thoughts is how I sort of view the world, and I think that that's kind of what we need to do. So I'm going to sort of talk about the digital twin and virtuality here with respect to, so why do we want to do this sort of thing? So if I look at a timeline and I have a physical product at time 0 plus X, okay, one of the big uses of the digital twin is simply replication. If I don't have to be in physical possession of the product, and in point of fact, if I have a digital version, I can instantaneously and simultaneously transmit it to people all over the world, then there is real value in that. I mean, there's a reason that manufacturing plants have their foreman shop over the floor so they can see what's going on. So I want visibility of my physical things with my virtual products. And so replication, if all I had was replication, that's a value. But where I really think you're going to get value out of the digital twin is what I basically call front-running simulation. And this is the idea that the digital twin really can be a time machine. It can let you look into the future. And so where I see, with the massive amounts of computing power that we have coming online, is that we're going to basically be able to, at every time zero, take the data from what's actually happening in the physical world and run the projection of what's going to happen in the future. And my intent then is what I want to be able to do is to have the system give me probabilities of things that are going to happen so that I can avoid having, for example, in a factory, if there's a glitch on a robot, and in an hour I'm going to have a bottleneck, I want to fix that before I have the bottleneck, okay? Again, the intent here is not to reduce the time from failure to remediation. It's to prevent the failure to begin with. And so I perceive that having the computing power that we're going to have is that we will have basically a simulation of the digital twin running in real time, taking data from what is existing from the product in the physical world, and then projecting outward to look into the future. Now, the other thing is I can also reverse that and go back into the past, which is why I have time 0 plus x. And so I can if there's a problem, run it backwards to see, where did I diverge from what I thought was going to happen to what happened. So again, I think the two things of the digital twin is replication and prediction. I mean, those are the two capabilities that we're going to get from the digital twin. We may not be there, in fact, we're not there today, but this is where the world's going. And again, what we've done with a lot of the simulations is we run some great simulations, we make the product, we throw the simulations in the drawer, and we never run it again until we make a next generation of the product. I think we should basically repurpose those simulations and run them over and over again. So where do I think we're evolving? And so if I look at information evolution against physical to virtual maturity, these are sort of the phases. The first phase was the fact that we basically had traditional manufacturing. As soon as we had an idea about a product, we had to put it in physical form. We had to write it on a napkin, create blueprints, create a prototype that basically allowed us to share that idea with everybody else. Until mind reading comes into vogue, although I have to say my wife does read my mind, to my detriment, but until mind reading comes about, it's really tough to share things with people unless we have this platform to be able to do that. The 2000s were interesting, as I view this as where we had a transitional time frame. And what's interesting is, so we had the digital twin come along, we had IoT come along, we had 3D moving from 2D to 3D, which is huge. It was a quantum leap in terms of our being able to visualize. And all this happened in the early 2000s. And so there's sort of a confluence of things that occurred that allowed us to basically be able to move along this particular path. We currently, what I say is in the conceptual ad hoc area. We have digital twins, but we have to do a lot of the work in pulling that information together ourselves from various sources. And so we have the idea of the digital twin, but we don't really have, systemic digital twins that exist. I take that back. I mean, there are some companies that have spent a lot of money doing that, but pretty much we're at the beginning phase of the digital twin in terms of the kinds of capabilities I'm talking about. I think the next stage is what I call the digital twin platform, the ability of pulling digital twins together, the disparate information. Good news about information granularity. We don't have to have the entire product in our existence. It's not an all or nothing proposition. But we have to do the work that nature does in terms of having atoms pull things together. We have to do that from a programmatic basis. So I see ours having replications. And then finally, this idea of what I call intelligent digital twin, I'll talk about in a second. But the idea that says that we're going to have platforms of systems that pull this data together for us and create viable digital twins. And not only digital twins of the system and the environment, but system of systems are going to come about too. And so we are on the cusp of complex systems, and yours is one example of that. I mean, it's not just a bunch of little toys in in a bathtub floating around. I mean, you've got really big problems in terms of being able to make all those parts and pieces work. You have a huge systems of complexity, and then you throw people screwing up, and it really gets interesting, right? So this is where I view kind of where we're going evolution. And again, what I would say is what we need to do is to be doing two things. One is looking at sort of concrete digital twins we can do today, but we really should be designing for the future kind of computing capability and storage and communications that are coming along on an exponential basis. I mean, we will not be able to take advantage of them unless we do that. So what are the impediments, okay? So hype potential. I mean, the problem is people, I have a digital twin of the world. Yeah, well, what are you going to do with it? And I don't think it exists. I can tell you as a former CEO, if you walk into my office and say, give me $100 million and I'll give you a digital twin, you ain't getting the money. I mean, and so we have the situation where people are hyping what digital twins will do and not focusing on, I drive everything from use cases, I drive everything from value propositions. And so you ought to be looking at low-hanging fruit that you know is going to work in order to show top management that they can do that. Organizational culture and inertia. So the fact that, we've been doing this all along. I have this problem with the testing people. They want to do physical coupons even though they could test digital twins. And as I mentioned this morning, retirement-itis. I am not going to risk my career and my pension for funding a project that I don't really quite understand because I'm not a digital native. So that's sort of an issue. Again, not having distinct use cases that create value. So it needs to create value for the organization and for the people that are buying your product. And if you can't figure out what that is, you ought not to do it. The lack of cohesion and integration. And I'll talk about that in a second. But the final one is cybersecurity. So the fact that this stuff is digital is not only great beneficial, but it's a risk. And so how do we basically protect that information, especially if we start to, first of all, have autonomous stuff running around in the world, and second of all, if we allow the digital twin to issue commands to the physical version. Huge problem. I mean, big problem just by collecting information from the competitors or people that have ill intent. That's a bad thing. But when we start to basically allow our digital twins to give instructions to the physical version, cybersecurity is paramount importance, and it does scare the hell out of me. And so I think one of the biggest problems is what I call cohesion. So cohesion has always been a characteristic of the digital twin right from its inception. And the idea of cohesion is the fact that if I change one thing, it needs to reflect the physical world. So programmatically, I can lengthen a steel beam by 1 meter and not add any weight at all if I haven't programmed it correctly. I can't do that in the physical world. If I add one meter of length, I get a corresponding increase in weight. And so we've got to basically have the virtual world have this capability of cohesion that the physical world has. So interoperability requires cohesion for these sorts of things. It requires it for internally, so within the individual product itself. So my example of lengthening an iron beam, you've got to not only lengthen add length to it, but you also have to have weight. But where it really gets interesting is that externally. And so if I have 3 digital twins and I basically fuel the fuel tank in this plane and I have an engine and I have a fuselage, not only does the fuel have to increase in the fuel tank, but the weight of the plane has to increase. And so I got to have cohesion across the entire digital twins, and it has to basically reflect what the physical world will do. So how do I get cohesion enforcement? Okay, so in terms of physics, I get it simply by the fact we live in a physical world. When I add atoms to things, I get cohesion, okay? Because the atoms basically do that for me. In the virtual world, we have to have information inputs and digital processing. So we've got to program that cohesion in. And again, this was a huge problem in terms of the virtual world of being able to enforce that, what we get for free in the physical world. So it's one of the disadvantages of the virtual world, but the advantages of information, I will contend, outweigh that, but we have to take that into consideration. What's the potential of digital twin cohesion solutions? So ad hoc custom software. So I mentioned the big oil field experience. They spent a huge amount of money to basically take all the different systems and connect them all together programmatically. Big bucks, okay? But it works. I mean, I can write ad hoc custom software, and that works. You heard sort of standards. So ontologies, and not necessarily, ontologies that have only one thing, but a mapping of ontologies. So you call that a gear, you call that a sprocket. I mean, we need to have ontologies that allow us to understand that they're the same thing. And then what I call method call semantics, okay? I don't really care what you do in your digital twin, but when I want information from it, we have to have common and implemented by APIs, but common method call semantics so I know I can get the information that I need. So standards, my only problem with standards is they take a long time to develop. A lot of times they're political, and the question is whose standard is that, and do people follow the standards? Harmonization is another way of getting it. So we all agree we're going to do something in order to be able to share information. That's probably the quickest, but it requires us to cooperate, and people aren't the greatest at cooperating at all times. But I think we're going to see more harmonization, and you certainly saw that before there was STEP for CAD. You saw companies being able to move CAD from one company to another, assuming that they had cooperated. And then finally, middleware. So companies producing middleware to be able to pull that information and being able to do that, the connection. And then finally, where I see it's going is people actually developing platforms. So NVIDIA is doing a pretty good job in that. Facebook, I don't think that they necessarily think reality is something that their metaverse needs to follow. And I got to tell you, the first person that designs a flying carpet in metaverse is going to lose a lot of money because can't do it. So I see platforms coming into play to be able to do that. So one of the things early on I said, we need to look at tests of virtuality. I mean, how are we doing with this? And with all due respect to Alan Turing, he got it wrong, okay? We are probably never going to see computers be intelligent as human beings. In fact, we really don't need to. I mean, we don't need computers to replace people. We've got plenty of people, okay? What we need to do is have computers be able to assist us in making better decisions. So, but on the flip side of that, in terms of things that aren't intelligent, okay? So the inanimate objects, I think the computers will be able to model and simulate everything else but human intelligence. Now, I just mentioned that in the digital twin of people, it's digital twins of their physiology, not digital twins of the crazy ideas they come up with, okay? So we will be able to model that, but not that. So how are we doing? So I basically defined these tests, visual, behavioral, reflective, and I just added a new one in a paper that's coming out, predictive. So visual is if I look at the digital twin and I look at the physical ones, I can ask to do anything visually, take it apart, whatever. If I can't tell the difference between the virtual one and the physical one, it passes that test. When I first proposed that, you could tell the difference between a simulation and a physical one. Today, I keep having to ask, is that real? Or is that a video? Or is that a simulation? You can't tell the difference today in terms of visualization. Behavioral, so I can ask the physical thing and the virtual thing to behave. I can apply forces to it, and if they both behave the same, it passes the behavioral test. We're doing pretty good at that. I can show you examples of crash tests of vehicles where you can't tell the difference in terms of the crash test of the virtual auto versus the physical auto. Crumple zones are all the same. They react the same way. Reflective is when the physical version changes out in life, engine RPMs change, we're going to see that reflected in the virtual one. In certain areas with IoT, we get that today. And then finally, the predictive one, the one I sort of added, is that we predict what's going to happen with the digital twin, and then we wait to see if the physical reality becomes the same. And I mean, the problem with that is we've got to wait for each clock time to do that. But in certain things, we're getting pretty good in terms of predicting. If the system doesn't predict, it may be good for reflection, for basically being able to replicate seeing that information, but I really want systems to predict. I mean, they need to match reality. If they don't match reality, we've got something wrong. So I'm just going to finish by talking about what I think the intelligent digital twin is versus the current version. And first of all, the current digital twin is passive. I mean, we basically sort of give it instructions. I see it being active and our AIs and machine learning telling us what we need to do in terms of being able to create capabilities. The current digital twin is offline. I mean, depending on kind of what the use case is, we may be batching that information, where I see the intelligent digital twin as being online all the time, so it's going to be active. We give the current digital twin goals. It'll be goal-seeking through AI and machine learning, goal-seeking and minimizing resources. And finally, we can predict in the current digital twin if we have the right data, but I really want it to be anticipatory. I want it to say, hey, dummy, if you keep doing that, you're going to basically crash this vehicle in the next 30 minutes. So it needs to basically be a little agent sitting on our shoulder telling us what we need to do. So, wait a minute, I already moved. So these are selected publications. They're available on ResearchGate. The first two are probably the seminal versions of digital twin. The white paper, interestingly, has got over 1,000 citations in academic papers, which is really surprising. But that was sort of a quick white paper on digital twins in manufacturing, which is why a lot of people say, well, you really started this thing with digital twins in the manufacturing area. But really, the first instance of it was for SME, and it was for the use of it in the support, because I always feel sorry for the poor support people. I mean, they get the product, go fix it. Well, what do I do? You know, what's it supposed to do? How do I even disassemble it? So I think that there's huge opportunities in that particular area. So with that, we may have a couple of minutes for questions, and I'd be happy to entertain them. Thank you.
Can you catch?
Can you throw that far? And you can, yeah.
Thank you very much for a very inspirational talk. I have two questions.
Okay.
When you spoke about platforms, you mentioned NVIDIA and you mentioned Facebook. You did not mention Epic and the Unreal Engine. It's one of the game engines that, for example, is used in the city of Göteborg for their smart city. Would that qualify as a platform or a generation of platforms? Yeah,
the gaming platforms are really kind of interesting. And I think that you're going to see the gaming technology be applied here, okay? Now, you won't be able to kill people and you won't be able to fly, but if we basically, be able to reflect what reality is, I think a lot of the gaming engines in terms of how things react is pretty darn good. I'm not as familiar as what they're doing in digital twin stuff, so I didn't mention them. I just talked about the two companies that have said, put a stake in the ground to say, we're going to do digital twins of business or industrial kind of equipment. But I absolutely think that we could learn a lot from the gaming industry. I agree with you.
Yeah, thanks. The second question is there an overlap between your intelligent digital twin and the cognitive digital twin?
And what's the other one?
The cognitive digital twin of this
I'd have to say, and I'm sure Ahmed is going to basically be able to send me his papers on it. But I suspect there's some of the same kinds of sorts of things that are there. I'm really not an expert to be able to talk about that. But stay tuned. I'm sure you'll send me papers, right? All right. Okay. And there's a pass. All right.
Okay. Thank you for your talk. I have a relatively simple question and an example. So you mentioned in your slides that the digital twin has to be going over time, so it's a life cycle idea.
Yes.
And I was wondering how you see the transition of the different physical twins over time, and so the flow of data. And the example that I have is, for example, in a construction building or in a product, you composed of smaller parts, and in our circular economy we are reusing the parts. But if we cut off the QR code with the digital twin identifier, then we lose a part of our. So how do we work with these components of those subcomponents?
Yeah. So the integration or interoperability piece is, so those of you that are doing research, huge area that I think is an opportunity. I mean, that is the issue of not only sort of throughout its life cycle, but how do I create, build up componentry digital twins, and then the system of systems complexity is really huge. But I guess from the standpoint of the technology, I'm pretty comfortable that that's going to come about. I mean, we have to do that if we're going to have integrated digital twins of major things. And I've seen examples that use the first thing that I talked about, which is ad hoc custom programming. I mean, they basically just brute force, take the different kind of information digital twins, and they basically provide their own interface to that, and they build the digital twin out of that. So, but that's expensive. I mean, we need to get to where it's plug and play, if you will, to be able to have that integration. But it requires everybody to in fact, follow cohesion, because you really can't, we're going to have to have an element of either trust or some sort of verification that that's going to happen. I would love to say, yeah, it's going to be standards, but I just seen standards evolve so slowly that I think that's tough. I go for the harmonization and building platforms where I think that's going to happen. Does that answer your question?
Yes. Yeah. Thanks.
Okay.
My throw is really bad, by the way. I can try. All the way back there. I'm gonna do it in. Can I do it in 2 times? Can somebody in the middle?
Yeah.
Hi. So I was thinking, what next with the front-running simulation? So what is the next stage of front-running simulation? My question is, if there is going to be, if the front-running simulation is viewed as a evolution in time, and if different worlds are running on that, like if different evolutions are happening, would there be chaos in the next stage?
I'm sorry, would it be what?
Would there be chaos in the next stage?
I don't think so, because this is sort of driven by business value. So I don't think people are going to build chaotic systems. They're going to need to build systems that provide value, or they're not going to get the money for it. But again, and I don't mean that evolution was a lockstep evolution. Some companies are already built their own platforms, so it's already going to depend on the organization and where they're at in terms of their value. Some companies haven't started digital twins at all. They don't believe in it. The testing community, as I said, is a huge problem in terms of believing in digital twins. One of my sort of side contentions is additive manufacturing is not going to catch on unless we can basically do our testing on the digital twins that come out of it. Because like the cast iron example is that every additive manufacturing part is unique in terms of how it was. So we're going to have to collect that information and be able to create a digital twin. One of my premises is that the best way to know whether a product really meets its criteria is to basically test it to failure. You can't sell a whole lot of those. So, but if we could test a digital twin to failure, that would be a proxy for the actual product, and we'd have a great deal of confidence, and it would be far, far less expensive than the mechanisms we use today.
Yeah. Thank you.
Any other questions? It won't kill you. Throw it.
Thanks. And actually, I just want to highlight, we had an additive manufacturing demo outside with a digital twin, which was nice that you referenced it. And thanks very much for your talk, Michael. I was kind of wondering more about the aspect of explainability, because in a classic twin, you have a physical thing, and then you have a virtual copy of it, and there's some explainable relationship between the two. But I think in the real world, we often don't know a lot about the physical thing that we're building the twin of. And do you see that as an important constraint or a challenge or a problem?
So again, it goes back to the use case. So because information is granular, I mean, if it is something that I need for the use case, or I'm measuring it, or I'm relying on it, then we got to understand it. But if it's so for example, let's say it's a gauge setting in a valve. Okay, if I don't care about it, okay, I don't really need to collect that information. So what's my use case? Where does it give me value? And then I'll tell you if we don't have that information, whether it's a problem or not. In fact, it's a problem if we need it. So again, because information is granular and it's not a whole all or nothing proposition, you know, we can select the things that we're interested in, but when we do, those things have to match our physical things, or else we have, you know, pretty pictures. We don't have a digital twin.
Yeah. I was thinking more in the direction of sourcing information from a variety of sources.
Well, that's funny you should mention that. So I get a lot of pushback from supply chains to say, that's proprietary information. I say, wait a minute, I'm buying the product, I'm going to have it. Why is that proprietary? The dirty little secret about supply chains, it's what's the most non-conforming product that I can send you that you'll have to take because you need it for production. And so my contention with supply chains is transmit me your digital twin, and I'll tell you whether to ship me the physical one. So I think that's a great opportunity. Companies that have great quality don't have a problem with it. Companies that are, you know, they want to basically have the product show up at your loading dock, surprise, and you have to deal with it. So I think that is a really good point, and I would love to see sort of people buying stuff to say, you know, transmit the digital twin, and I'll tell you whether or not to ship me the physical version.
Thank you very much. Back again. I'll try it this way.
You should put that in a beach ball. I mean, and that would really...
Thank you for such informative slides. My question is related to cohesion in the family of systems. So for example, if I have multiple systems and each system digital twin is designed on a particular middleware, and we have to integrate or perform the cohesion across that family. Do we need to design a custom middleware across the all family, or do we need to change the middleware of each particular system? What should be the approach related to that?
So when I'm talking about middleware, I'm talking about, if you're familiar with ERP systems, you know, there are companies that sit in the middle and basically do that. I think it's an opportunity for companies to sell middleware. If you're doing it yourself, then you're in the ad hoc custom programming area. So I'm going to be a little more comfortable with middleware that a lot of people are using to work the bugs out of than my own custom programming. I'm sorry. I'm probably not. That's probably the wrong thing. It's probably going to cost a lot less if I can find a middleware company versus having to do ad hoc custom programming. But I'm also going to have people, you know, sort of the share of the commons finding bugs in terms of what the middleware is if it's a company that does it for a living. So I'm hoping that we'll see companies develop middleware to pull different data sources to create digital twins.
Okay, thank you. Gotcha, yeah.
Good job.
I'm doing multiple proof of concepts, building multiple digital twins, and I find that I have to build half of them with CAD data and half of them with tessellated data. Basically half of them with GeForce cards from NVIDIA and half of them with the Quadro cards. To prevent me from keep having to build every twin twice, do you have a preference?
So I don't have a preference, but it would be nice if something sat in the middle so that you didn't have to worry about whether it was a tessellated or it was a CAD version. And you know, STEP really doesn't get you there. But that's why I say we're really in the early stages of this. The kind of problems that you have, I saw early in for example, local area networking business, where the same sorts of inconsistencies between, say, Novell and Banyan and 3Com existed, and you had to sort of build your own to there. But fast forward, you know, a decade, and all those problems got sorted out, and there was consistency, you know, so that all those systems communicated with each other. So if you want a business, go ahead and build one of those. Otherwise, I think if you wait a bit, my suspicion is that somebody will look at that, because that's a common problem. And it's not only just the CAD data, it's is it NX, is it CATIA? I mean, so you've got or Autodesk, so you've got that problem even within different systems. Now those you can move to STEP, but do you really want to do that?
All right, thanks.
So here's the hook. I'm off.
So thanks for all the questions. Thanks for a very inspiring talk. And I think I can say that on behalf of the University of Technology, on behalf of Philips, on behalf of Signify. So yeah, I like the content of what you have been saying, but I also like the passion and the energy that you radiate. So I think this was very nice to listen, and well, you could see it from the questions, and I'm pretty sure that people in the audience will get, you know, continuously inspired by the content of what has been presented. And I'm thinking of students, professors, the researchers from Philips, from Signify, and maybe also the broader ecosystem of, you know, Brainport Eindhoven.
Thank you.
So, yeah, with this lecture, you tap into a long history. I think Henk mentioned it. The first one was 1977. So you join as a presenter here of this Holst Award a team, a league of people, famous scientists, researchers, innovators at large, who, you know, on a global scale, who have made impact in their field. Personally, for instance, I was here in the audience myself in 2008 when Nakamura talked about the blue LED. You know, that I'm from lighting, and that really revolutionized the whole lighting business. By the way, Nakamura-san, 6 years later, got the Nobel Prize for Physics. So it's also kind of a nice place to be here.
So my colleague at NASA called this the mini Nobel Prize. So,
exactly. That's exactly what it is. But let's now move to the very official part of the handing over of the medal. But before I do that, I want to read a little bit, a small piece of text from the official report that the Holst Committee has prepared when they nominated you. I'll cite that, so I'll read it from a piece of paper here. And when I want to see things very clearly, I need to take off my glasses. The committee nominates Dr. Michael Grieves for his important contributions in the field of digital twinning, a concept he originated. In his work, Michael Grieves successfully combines research, systems engineering and manufacturing, and in this way plays a pivotal role in driving the 21st century transformation.
Thank you.
Well, I cannot say that better. I think that is really what you did. So, let me take that away. On behalf of the Holst Committee, Dr. Grieves, it's an honor for me to hand over the Holst Memorial Lecture Award to you. And as you will see, that award contains a picture of Gilles Holst. It's made by a famous Dutch artist. And let me hand it over now to you.
Heavy. Yeah. Was this a cast iron?
Yeah, it's more heavy than its digital twin.
Yeah. Thank you very much. I'm honored to get it. I think it's sort of a fabulous thing that you've got going here, and I'm just sort of highly honored to have been a recipient of this. Thank you very much.
Okay, we are very honored to have you here. Thank you. Yeah, and with this, we get to the end of this session. I hope you enjoyed it as much as I did. I liked the interaction. I like the enthusiasm of the public. We will have another session 1 year from now, so you're all invited. So put it in your agendas. And I understand that there's still a reception here after we close. And that will be the nice opportunity also for you to personally congratulate Dr. Grieves. Thank you very much.